log, semi-log graph. I hope that is clear. Is that clear, class?
Yes.
Yes.
Please, okay. Do you have your graphs with you? It's very important that you know how to. You can actually able to read these graphs, and you are able to use
Yes.
them. Okay, fine. So, as I said, Bode diagram has two graphs. One is a magnitude, which is dB versus log frequency, and another graph is phase versus log frequency. And all these two graphs are plotted on the same semi-log graph. And example is like this. So here you can see we have 20 log our transfer function, which is magnitude in dB versus log omega. So it's already in log form. So the way you do it, you just plot your omega, don't change. And then here we have phase against same x-axis. So you can see we have two graphs, one magnitude graph and another one phase graph. So this is actually an example of Bode diagram plot or Bode plot. Sawa. And since our magnitude is in log form, then it means all these factors, if it's a product, then the log will be actually a summation, and division will be subtraction. So whenever we are drawing these, we'll be actually adding this instead of multiplying, because we are dealing with log in decibel. We are dealing with magnitude in decibel. We'll see in a short while. So one of the factors is actually this one. We can split this, and then we can say we have this factor, we have that factor as a 0, this factor as a pole, and this factor as a complex conjugate of a pole or a 0. So we'll discuss this 0 and a pole, and then we'll just I'll show you how to plot this. So you can either look for magnitude for every omega, or we can actually look for approximate of these factors and plot them as you are using that transfer function. So we'll tackle this first, k over s like that, and then 0, and then pole, and then later on we'll look at an example how to plot these diagram. So for a constant term or a pole or a 0, what we do is we say, remember we say we actually get magnitude in decibel, which is 20 log of that, its magnitude, and this magnitude will have 20k. This one, it will be just omega n. When we open this, since it's a division, then it will be just minus 20 log omega n. So if this is dB, we can see that this equation, it's like y is equals to c plus mx, the famous straight line equation, where c is the y-intercept, and m here, this is, sorry, that is gradient. So this one is 20 log k minus 20n log omega. Sawa sawa. 20k log omega. So from here, we know that we can say at omega is equals to 1, if omega is equals to 1, here it means we have 20 log k. So if we have omega is equals to 1, it means there is a point here which is just 20 log k here. If this is 1, so this must be 0.1. So we can also look at, let's say at omega 1, so we have dB1 is equals to 20 log k minus 20n omega 1, and dB2 log k minus Guys, are you with me?
Yes.
Okay. So if we say for omega 1, let's say we have omega 1, then it will be like dB1 is equals to 20 log k minus 2n from this equation, log 1. And dB2, it will be like that. Why are we doing that? We just need, I just want to show you the next part of that line. We know we have at omega is equals to 1, we have a point which is 20 log k. So if we have omega 1, then dB1 is equals to that, dB2 is equals to that. If we were to minus these two, then these two will cancel. We'll have 20n log omega 1 minus 20n log omega 2, like that, which is just 20n log omega 1 minus divided by omega 2. So say we have omega 2, say omega 2 is just 10 omega 1, then dB2 minus dB1 is equals to 20n log 1 over 10. Inverse of log of this is just 20n log 10. So it means if there is a difference or an increase or multiple of 10 between two frequencies, then the gradient is actually minus 20n, where this depends if it's a square or just one pole. So if it's just a pole, one pole, then it means it is minus 20 dB per decade. Per decade means per every 10 between two frequencies. Here we have omega 1, and then after 10 times per every 10, That's what we mean, minus 20 dB per every decade. So if we were to complete this, it means this line will come like that, which is minus 20 dB per decade, passing through point 20 log K at omega is equals to 1. So whenever you see something like, let's say 5 is equals to j omega in that transfer function, then first thing you need to do is get 20 log 5. I think this is 14 dB, and then locate this point at omega is equals to 1. So if this is 0.1 and this one is 1, this is where is omega. So you locate this point. You say, okay, this one is 20 log 5, which is 15. Align, and this point will have minus 20 dB per decade passing through this point because of this factor. Sawa? Class, is it okay?
Yes.
Okay. So another factor is a 0, a real 0. If I go back, you can see we have this, and then we have a 0 here. So 20 log magnitude of this j omega tau. So this is 20 log of magnitude of that is just 1 omega squared tau squared a half, right? So if this goes here, we'll have 10 log 1 plus omega, like that. Now we can say for low frequencies, it means this is less than 1, right? For low frequency, say omega, this is much less than 1. So if it's much less than 1, it means we just have 10 log of 1. This will disappear. So it means for this factor, for lower frequencies, we have a 0 dB line. So for lower frequency, we have a 0 dB line like this. Let's say this is 0 dB. Up to a certain point, we see. So for high frequencies, which is much greater than 1, it means we'll have log from here 10 log like that, which is just 10 log omega that plus 10 20 plus 20 tau. So you can see this is also like mx plus c. It's a straight line with this factor and that factor. Sawa?
Yes.
Okay. Now, if omega is 1 over tau, we say that it's a corner frequency. If it's 1 over tau, and you substitute it here, it means this thing, it will just be 10 log of 1, which is 0 dB. So this low frequency line is shared this point is shared with high frequency line at omega is equals to 1 over tau, corner frequency. After that, it will go with 20 dB per decade, like this. Or this is positive. Is that okay? So for a real zero, if you are to plot these approximate lines, we'll have a 0 dB line, 0 dB, going up to a point where omega is 1 over tau. We name it corner frequency, and then after that, we'll have a slope of 20 dB per decade. 20 dB per every 10. For real zero, if you apply same principle, you'll have something like this, 0 dB, going up to a point here, and then instead of going up, it will go down minus 20 dB per decade. If you apply same argument for real zero, you'll have minus 20 dB per decade, with a zero line for lower frequencies, and then for higher frequencies, you'll have a slope of minus 20 dB per decade. For complex conjugate, same as this, but if it's a pole, then it will be as a 0 dB, and then at corner frequency, it will be, if it's a 0, it will be 40 dB per decade. If it's a pole, it will be minus 40 dB per decade. As an example, okay, procedure for plotting Bode plot. First, you put it into time constant form, obtain these frequencies, corner frequencies, these ones, where omega is 1 over tau, like that. And then if you have this term, so you deal with this term first, you mark a point of 20 log k at omega is equals to 1. If it's n, if n is 2, then it will be 40 here. But most of the time you just have like a pole, one pole at the origin, or 1 0 at the origin. That's how. And then draw a line with this. If it's a pole and a 0, it's a plus, until you get into the first corner frequency. And then from there you add them and repeat the process. I'll show you how to calculate the phase later. So for this example, you need first to express this into time constant form. So you have 2000 s plus 1 over s. So you say you remove, you factor 10, so you have s over 10 plus 1, s over 40 plus 1. Since we factor 10, we'll have 10 here and 40 here. So that one and that one will be 5. So you have 5, 1 plus s, 1 plus s over 10, 1 plus s over 40. since we are dealing with frequency, we set S into j omega. So we'll have 5 over j omega, like that. 1 plus j omega as a 0. 1 plus j omega over 10, and 1 plus j omega over 40. So we know how to plot this, that, and that. This is a real 0, and these two are real points. So first, you can say corner frequencies. For this 0, the corner frequency is which the denominator of omega. So omega is equals to 1 radian per second. And pole, we have this. Omega is 0. Here, omega is 10. And there, omega is 40. So these are the corner frequencies for zeros and for pole. First step, you plot this. We know 20 log 5 is 14 dB. So you mark this point at omega is equals to 1. Sawa.
Yes.
So if this is 0 dB, if this is 0 dB, and this point is 0.1, next one is 1, and then 10, and then 10 to the power of 2. So at 1, we mark 20 log 5, which is 14 dB. Say it's this point. And remember, we say this is there is a slope passing through this at minus 20 dB a decade. So if this point is 14 at 1, at 0.1, it's which point? So that we have minus 20. So that this line is actually minus 20. So at this point, which line? Which point, sorry? Someone? Yes?
34.
34. So that we can have minus 20 dB. And dB because of 0.1 to 1. So 0.1 to 1, it means there is a frequency change of 10 times. So this line will come until it reaches at 1. So the next corner frequency is this one, right? It's this one due to what? Due to a real 0, this point. And we know this real 0 is actually 20 dB going up. It's 20 dB going up. So we know at this point we'll have a 20 dB going up. This is due to 0 of 1 plus j omega over 1. But this point, this line also goes downwards like this. And this is minus 20 dB. So 20 dB plus minus 20 dB is actually a 0. So the resultant between this and this, because this just goes like that. So contribution of this into 5 over j omega is actually a 0 dB. So this line will go until it reaches next corner frequency. So the next corner frequency, remember first one was 0, then 1, next one is 10. So this line will go until it reaches at 10. From there, we look at the contribution of this pole. So this line will go until it reaches at 10 omega 10, which is a corner frequency due to a pole. From there, we need to add contribution of this, and we know a pole will go to minus 20 dB. So from here, it will go like this, minus 20 dB. We just know 0 plus minus 20 dB is just minus 20 dB. So we'll have a minus 20 dB until it reaches next corner frequency. And that corner frequency is what? Someone? Hello?
40.
40.
Okay, at 40. So this is minus 20 dB per decade. This is 0 dB. And this is minus 20 dB. So minus 20, and then you have 0, and then you have minus 20 dB. So the next is due to contribution of what? Of a pole, which is also minus 20 dB. So minus 20 dB due to a pole at 40, and this minus 20 dB due to a pole at 10, it means we have what? Minus 20 plus minus 20 is what? Minus 40 dB per decade. So this one will go on because we don't have any frequency after that. So we have minus 40 dB per decade. So this is how we plot Bode diagram using asymptotes or approximation of lines. So for phase, you need to calculate individual phase of each factor. From the time constant representation, which is this one, you can see we have 5 over j omega, 1 plus j omega over 1, 1 plus j omega over 10, and that over 40. So you calculate phase for each of these contributions. So first contribution is 1 over j omega. So this is just constant. We know 1 over j is just 90. So we have minus 90, 90, 90, 90 like that. So due to 0, we know it's tan inverse this part, imaginary part, over real part, 1. And since it's a 0, it means this is plus. So all these are plus. So you just choose frequencies, logical ones. We know it's from 0 to. So you choose frequencies between your scale, the magnitude scale. So from there, you plug in into your calculator 0.1 and get an inverse 1 like that, like that, like that. So due to this real pole, it is actually, since it's a pole, then you need to have minus. So minus tan inverse. This is 1 over 10, right? 1 over 10 is 0.1. So real, imaginary over real. So minus 1 tan inverse 0.1, you get the faces. Same thing with this, and then you add that one plus that one plus that one plus that plus that. You get your total face angle for that transfer function. Remember, this is g of s. We are assuming it's a unity feedback. Our h is equals to 1. So you add for 0.1 frequency, the total angle is that. For 20 is that. For 1,000, it's like that. Then you plot this graph and these values against frequency. So you'll have something like this on one semi-log graph. Remember, this point here is 20 log 5 at 1, like that. So you draw like that. This is approximate. So you just use approximate, and your graph for the face. So this is Bode plot for that transfer function. Any question?
Excuse me, sir.
Yes.
Kindly review how you plotted the first one, the one that we were having the gradients of dB per decade. Just review.
Okay. Where is it? Here. So our transfer function was what? It was 5, 1 plus j omega over j omega, 1 plus j omega over 10, 1 plus j omega over 40. Okay. We said we start with this 5 over j omega, and this is actually a point. There is a point which is 20 log 5 at omega is equals to 1. So you mark this point first here at omega is equals to 1. So there is this point here. So, but because of we saw that this also has a minus 20 dB line per decade. So there is a line which is coming, and this line must pass through omega 1 at this point. So 14 dB. So there is this line here. So hello?
Yes, it's okay.
Yes, it's okay.
Okay. So that line will move until it reaches the next corner frequency. So the next corner frequency is what? We have omega is equals to 1, omega is equals to 10, omega is equals to 40. This one, and that one. So, and this, the next corner frequency is omega is equals to 1, which is due to a 0. This 0. And this 0 is actually at 20 dB per decade. So there is a line at this point, there is a line going up like that. Here we have 20 dB per decade, and here we have this line passing through one at minus 20 dB per decade. Since we are dealing with log, then it means we can add this and that to get contribution of this and that just before it reaches 10 corner frequency of 10, which will at that time will add contribution of this. So this 20 dB and that is 20 dB. 20 minus 20 is what? It's 0 dB. So we'll have a 0 dB per decade. It's a straight line. It doesn't have gradients. So,
Yes.
0 dB per decade, not 0 dB line. So we have that one. It will move until it reaches at 10. Omega is equals to 10. Then at that point, we know there is a pole here. This pole, we know we have that pole. And that pole give minus 20 dB per decade. So that's why you see this line here. Until it reaches what? This is 10, 10, 20, 30, 40. At this point, this 40. So at 40, we have another pole, which is also minus 20 dB. So minus 20 and minus 20 will have a minus 40, a minus 40 dB. And this will go on because we don't have any other frequency. Is that okay?
Yes, it's okay. Wait, kulikuwa na hii swali.
Anyone else?
Excuse me, sir.
Yes.
Just a clarification. So when we were beginning at omega is equals to 1, we were using the 0 and we didn't consider omega equal to 0 at the pole, Ama?
No, we assume it's a very low frequency.
We assume which one is a low frequency, the omega equal to 0, the omega equal to 1?
The omega is equal to, okay, we assume, we actually assume 5 over j omega. That factor is actually contribution of a very low frequency.
Okay, is that arbitrary? So for all others, it's it sets a precedence, Ama?
That's how we plot.
Okay.
If you're plotting remember this is approximate lines.
Okay.
The dotted one here is exact. You can try to imagine you are plugging in 0.1 here, 0.1, 0.1, 0.1, and then getting what? Getting magnitude, and then you plot like that.
Okay, makes sense. So, thank you.
Please make sure you know how to plot it. Be sure that I normally bring both plots, Nyquist, you know those things we did transfer function of RLC circuits or what, the modeling, all those things. These are kind of questions which be sure you'll have a board plot or a Nyquist or what in the exam. Sawa. Anyone else? You can try and plot Another thing which is very helpful, other guys I saw in some books, what they do on the graph, on the semi-log graph, what they do, they plot first this graph like -20. They draw a line. You see, from here, let's say this is 20 to what? They draw a line right from 20 here, which is 0.1. This is 0.1, and this. So it means this is -20 dB per decade, right? They draw these lines first, and then when they are plotting these graphs due to factors, what they do, they slide this line to meet at that point. They slide because we know once you have these as a key on top of your graph, then you can actually slide this parallel to meet at your point. I wish I can show you physically, but I'll look at one of the videos and post. You can actually see what I mean. First, you draw these lines as your key, the 20 dB lines, -20 and plus and +20, and then when you need them, you actually slide with a ruler. You construct a parallel line with that, just sliding with, I think, a square. Is it a square what? A square ruler or what? You slide so that you have same line, rather than going and try to calculate. Okay, this is 10, then it should be like 34 here, so that I can get -20, something like that. So if you have these lines, you can actually slide them, and it will make your life very easier. I'll look for a nice video in YouTube and post this, how to use these lines when plotting. But I think it's clear how you can plot Bode plot. It's not hard. It's very easy. You need to do like 3-4 examples. Look at the examples and see if you get them right. This example is actually in one of the textbooks, and I think I have same one in the notes. Any other question? So normally questions come like, you need to plot this. You are given transform function, you plot this, and then later on you are being told to get the first margin and the gain margin. So what I need from you guys is, please read this. Please read this gain and first margin from the notes. We'll do it quickly tomorrow, and then move to polar plot. And then we'll have one class on Nyquist criterion. Is there any other question? And also, I'll request tomorrow we have 2 hours instead of 1 hour. Hello?
That's okay.
We need 2 hours so that we can finish. We can finish this. Any question? Polar plots are very easy. We do one problem, how to plot them. It's very easy, and then we'll move on. So tomorrow we'll tackle this and that. If we have time, I'll introduce this or finish this, and then we are done with 4 and 1. About the cut, I'll post numerical solutions only. Others you can check from your notes. I'll post for two cuts. One which majority did, and another one there were like four students which were not able, so I set a different cut. So I'll post those two cuts first, and then post solutions maybe by tomorrow, if that's okay. Any question? Will you send the? Yeah, I'll send the recorded video. Faris, I'll send. Yeah. And also, please inform your classmates that classes have actually resumed. Someone is saying, I can't see the calculation. Were you able? Other guys, were you able to see what I was doing?
Yes, we were.
Okay. So that's it. Let's meet tomorrow at 10. And if I can get 2 hours, I'll be happy. I'll send you solutions for the cut and also the video once it's ready. Okay. See you.